So here we are at the Tuesday chat. All right. Okay. Now I went around the room, did a homework check. I'm going to start doing that. I used to do it all the time, like 2 or 3 times a week. I would check for homework and I would give everybody stamps. So they had the front of the notebook and then they had a big stamp grid that I would fill in for each packet. But we don't have notebooks, so I kind of blew it off. But now I'm going to try and experiment between now and Christmas. I'll do experimental things towards the end of the semester to see if they work. So I'm going to go around. I went around today and stamped people's homework if they had them. And not a lot of people had it, but I think tomorrow they will. I'll give homework tonight. So really very few. So tomorrow I'll give you a homework assignment at the end. And then I don't know how we're going to do it on here, maybe before I start recording. That's what we'll do. Before I start the official recording, because I don't want people that are watching it to have to sit there and look at all that, plus FERPA, right? So I'll just have you hold it up to the screen, your homework, and then I can't really give you a stamp, but I'll like, okay, so I'll say, hey, that's 2 points or that's 1 point or whatever. So these are little dolphin stamps, and the stamp changes every packet, but yeah, so we'll try it that way tomorrow on the homework. We did this yesterday. Don't you worry about this. Okay, so speaking of the homework, let's look over the homework. We did this one in class yesterday. We derived the third orange. Looks like most of you are returning, so you were here for that. And then we did this problem number 3 where you're using the third orange. And then I want to knock off, I sent them to the board. This was homework, which like I say, only probably out of 50 kids that were there all day, probably 10 of them at the most did it. But that's okay. They didn't really, I hadn't really been pushing on that. I think tomorrow I'll get a lot more of a response. So this was a go into the board problem, this Spencer Rattler, which was the homework. So normally I would hit pause and let you all do it, but it's supposed to have already been done. So without wasting your time, let's go ahead and knock this one out. So I wrote this, I think, when Kyler Murray was the quarterback. I don't think Spencer Rattler was quite this fast. So we circle first, and then we label. So he's moving at 4 yards per second. That's V naught. The acceleration is 2 yards per second. And then the delta X is how far he went. We're supposed to figure out what his V final is. So actually pretty straightforward, right? We need a little drawing there. I tend to want to just skip the drawings on these early ones because the drawings aren't very complicated, but I want to get in the habit. I want you to get in the habit of doing it. So I'm okay. We already circled, so you can just put V naught, V final, V final question mark, and then just put A, put delta X. And obviously I'm looking right. And if it's on the board, you'd have to label it, but if it's just on your paper, you've already circled it. So that's good enough for drawing for now. Okay, so we're just going to use the third orange here. V final squared equals V naught squared plus 2A delta X. Hopefully you're just following along on your paper where you did this. If you didn't get a packet, if you don't have a paper packet, then they'll be on the front porch. I guess I'll set those things back out there. Well, we catch a little break here. The green kill pin comes out because, oh, not this time. No, that's not the case. I'm thinking of another problem. So we're trying to solve for, V final. Oh, it's already isolated. Okay, so all we got to do really is just plug and chug at this point. So I say, okay, V final. Then we're gonna scroot everything. So V naught squared, which is 4, so it's going to be 16 squared. I got to square the units as well. Yards squared per second squared plus 2 times A, which is 2 yards per second squared, times delta X, which is 15 yards. Okay, you'll notice that'll end up being yards. That will end up being yards squared over second squared as well. Okay. It has to, you can't add up two numbers. You know, it's like apples and oranges. So you have to, you can't add up two numbers if their units are different. You can multiply them, you can divide them, but you can't add them or subtract them. Anyway, you do all the number crunching on this, and this time the answer at the bottom of the page is correct. That ends up being 60 here plus 16, so the square root of 76 is 8.75 or something. Let's see, 8.7. Okay, so 8.7 yards per second. That's pretty fast. A yard is about a meter, and so we know Usain Bolt's kind of my my reference here. And so Usain Bolt's around 10, a little less than 10 meters, a little more than 10 meters per second. So 10 yards a second. So probably a little fast for Spencer. But okay, now we're going to knock off. What we're going to do in this time is we're going to knock off 5A, 5B. Maybe start to talk a little bit about 5C. 5B is as far as we got in class, and then I assigned, because first hour was behind for some reason. They're always delayed because they're always beginning of the classes because we got to sit through announcements, and then we got to sit through the moment of silence, and then we got to sit through, which I enjoy, morning roar, but it just takes up time. So that always puts first hour in, which is a disadvantage for them because then the other classes get to time working on homework in class, whereas first hour doesn't usually get that. So now we're going to look at 5A and B, and then what else we'll do? We'll maybe watch a short little clip of fighter pilots, and after that, I'll talk about the homework. There's something else we did. Anyway, it's on here if we did it. So here we go. First, look over 5A. This is we're talking about a rifle here. It's 80 centimeters long. It's about like that. If you can see my hands. So that's pretty good size. A little less than a meter stick. And let's go through it. Change my colors up here. Let's go to purple. So we got 600 meters per second. Now that is obviously it's a velocity, but is it V bar? Is it V naught? Is it V final? You know, you don't know for sure yet. I imagine it's not V bar. Occasionally it is though. And the barrel of the rifle is 80 centimeters long. Well, obviously that's delta X. At what average rate? Now rate does not mean, I had a student ask this, rate does not mean velocity. I know you learned in mathematics that distance equals rate times time. Why in the world they would ever teach you that, I don't know. That's ridiculous. I agree, it technically is correct, but rate, everybody then associates the word rate with speed. Rate is a change. Rate could be jerk. Rate could be acceleration. Rate could be velocity. So in this case, the average rate of change or slope, it just means slope, of change of the bullet's velocity. So now we're looking for acceleration. So the question is, what is acceleration? Okay. All right, so here we go. We're going to draw, so it looks like everything's occurring inside the barrel. So therefore that 600 meters per second. Normally when you see the word muzzle, and you talk about muzzle velocity of an object or a bullet, that means the velocity that the bullet comes out of a barrel. So they'll rate, guns by what's the muzzle velocity, and then it depends on the caliber of the bullet, but what's the muzzle velocity of this bullet in this gun. And this 600 meters a second seems high, but it's not really. It's these are things we talked about in class. The speed of, by the way, that's V final. The speed of sound is 331 meters per second. Probably write that down. That's pretty important. And that is considered Mach 1. Mach 1. Named after a guy named Ernst Mach in the 1800s. He was actually an influencer of Einstein, Einstein in his studies. Yeah, so they named it Mach 1, the speed of sound, in honor of Mach, who studied waves and things like that. So Mach 1, so if that bullet's coming out at 600 meters a second, that's getting close to Mach 2. So in the movies, you know, someone says bang, bang, and ouch, it's more like ouch, and then you hear the bang, bang. Okay. Now, you know, 22s, if it's a 22, it's not going to come out that the velocity, you can look up the tables there, but the velocity of the bullet coming out of a 22 is probably subsonic. I don't remember exactly, but for a 38 or, you know, 44, I mean, all the larger, and the shotgun, this is about the right speed for a shell coming out of a shotgun. Out of a rifle. I mean, a rifle, not a shotgun. It's a different situation. Okay. Oh, and then we had this discussion. I'm trying to mimic the discussions from today. So here's my barrel. We got a bullet in here. And the question I asked the class was, how does that bullet then, if this is my bullet, how does that bullet get accelerated? What accelerates that bullet? There's my striped bullet there. What accelerates it through the barrel? What do you guys say? Once you pull the trigger, what accelerates the bullet through the barrel? Or what's the cause of the bullet then racing through the barrel? Anybody want to hazard a guess? I don't know if you all shoot guns at all. We are in Oklahoma. I went out and shot. I shoot guns with my buddy, and I bought a new pistol, so I wasn't ready for the kickback. There's always recoil. We'll study recoil. We'll study the physics behind recoil. But man, it just ripped my hand. The recoils in these things, and that wasn't even a huge gun, 9mm. So, but these shotguns have some big kickback. Anyway, so what causes that bullet to accelerate through the barrel? We got 8 of you here. Somebody's got to say something.
Displaced air.
Oh, sorry. Let me turn you up. Okay, say it again.
Displaced air.
Yes. Well, it's an explosion, right? So there's a miniature controlled blast, the gunpowder, right? And it's expanding air, right? It's the expanding air of an explosion. That's a whole set of physics of those formulas behind everything we do. It's got formulas, but behind that expanding gas, we'll discuss that more tomorrow. But so behind this bullet, there is all this expanding gas. I'll make it green. That the bullet has nowhere to go. I mean, it has somewhere to go. The only way it can go is out that barrel. So it goes at tremendously high accelerations. And then we got to talking about how the bullet comes out of the barrel. And there's something called rifling. Back in the Revolutionary War, these were more like musket type things or solid bore. They were called solid bore shotguns and not rifles. Now, rifling didn't come into play. They had a student was telling me this today. He looked it up. He said, well, they started learning how to rifle back in even the 1500s, but it wasn't into production until about the mid 1800s. Now, what you do in your rifle is you make it like Okay, I'll show you. Like a spiral. So the inside bore looks like this. So the bullet is forced to rotate and to spin. Now, why would you want a bullet to spin inside a rifle?
Travels farther.
It does. It travels with more accuracy. So it's like a knuckleball. If you don't if you have a solid bore, the bullet comes out as a knuckleball with no rotation at all, and that can be haphazard. It doesn't have much stability. When something rotates, like a frisbee, if you're going to throw a frisbee, you want it to spin, right? The faster the spin, the more stability. Or riding a bicycle, and it's the whole physics of it. There's a gyroscopic effect. There's conservation of angular momentum. There's torque involved. All of these physics, and this is a second semester AP physics concept because it involves calculus. But that bullet, the omega on that bullet is huge, and this is not a circular motion problem. But it's because that bullet spins, like the faster you ride a bike, the easier it is to stay propped up, right? The easier it is, you can take your hands off the wheel, off the handlebars, and just kind of kick back, because fast spinning tires give you a lot of stability. They have a tendency not to change their axis, and that's called conservation of angular momentum. When you start riding a bike as a kid, the hardest part is getting going. Because that was the hard part for us when I was a kid. So once the wheels start going, same thing with a frisbee or with a bullet, when it's rotating, and I have video of this too, I need to find it, but of those bullets when they come out, how fast they rotate. That's not about this problem at all, but I'm trying to mimic the class discussion. I actually, if I have any kind of discussion in class, I jump on it because they don't say a whole lot. We'll get to that. We'll get to this again later. So this is delta X, and delta X is 80 centimeters. Oh, you know what I'm going to do? Right off the bat, I'm not going to fall for that old gag. I look at the answer. I want this thing in MKS system, meters, kilograms, seconds. I don't want to deal with CGS. So I'm going to go ahead, because I know I'll forget later. I'm going to make that 0.8 meters. Okay. It's a quick, it's not worth drawing you to analysis. It's just a quick conversion. That's the oldest trick in the book in physics, on physics problems, is you throw. I don't like, myself, I wasn't doing it to trick you. I don't like to use decimals. Like, I don't like to, it's not how people talk. You don't say, well, 0.8, maybe you do. You say 0.8 meters, you say 80 centimeters, I don't say 1/3 of a foot. I say 4 inches, right? All right. Well, maybe you do. I don't know. So this then, the velocity, let me blow this up a little bit. The velocity coming out of there is V final in this case. So V final is 600 meters a second. Or Mach 1.8 or something like that. Sometimes I'll say, well, this is moving at Mach 4, and then you'll have a conversion. Okay. Then we're going to have to assume that V naught, the bullet in the chamber, before the explosion, before you hit that gunpowder, V naught is 0. Okay, so we're trying to find acceleration, and you guys can chime in and Bennett said something. Oh, he said displaced air. Yeah, it's a concussion wave, right? I mean, it's like in any kind of explosion. I hate to bring this one up, but the Merle bombing, glass shattered all over the city. It wasn't because of shrapnel. It's because of the concussion wave, because it's simply air molecules. I mean, the air molecules in your room will kill you. Yeah, if the air molecules organize, they'll kill you. They can kill you if they want to. Because that's all really a blast wave is. Yes, there is shrapnel, but way beyond the shrapnel, way ahead of the shrapnel, is that compressed air. It's rarefaction and compression. It's how sound waves move. But this air it's random motion. But then here I am, I'm organizing the air. You hear my voice. So through my larynx and all, I'm organizing the air. Well, that's the same thing here. That is a concussion wave inside the barrel. So it's a huge standing wave that's instantaneous, practically. Okay, so let's write our equation out. We're going to use, once again, you get little points for this. V final squared equals V naught squared plus 2a delta x, and then bring out the green kill pin. That's going to be 0. Yes, thank goodness. And so we're solving for a. Now that's a little different. So in this case, some people are still having trouble with the remembering how to isolate variables. For the a, you're going to divide both sides by 2, divide both sides by delta x. And so we have v final squared over 2 delta x. Yes. So I box that in. That's my isolated equation. And all that's left to do is plug and chug. And it looks like my units are going to be nice to me this time. So nothing weird about that. So acceleration ends up being 600. You're working along with me, or you've already done it. Maybe you've not done it. Meters per second. You square all that, and then 2 times 0.8 meters. Now, I'll save you time. When you do this, the first time I did this, I thought something's wrong. I made a mistake on my numbers. But no, let me get that out of the way. First time I did this, it seems crazy high. So the answer is 225,000. If I remember this from last year. Meters, someone check me on that, but meters per second squared. Don't say anything unless I'm wrong. 225,000 meters per second squared. That's an insanely large number. Even 1 meter per second is a decent acceleration over time. But 225,000? That's why it seems crazy. Okay, let me tell you why it's crazy. And we had this discussion, all right? We talked about G forces, G. And this is, I've seen it both ways, but normally we consider this a lowercase g, because capital G stands for universal gravitational constant, and I don't want to mix those two up. So lowercase g, as in G forces, something called G forces. Okay, now I'm going to show a little video here in a second on this. I didn't show it in class, but I'm going to try it out on you guys. All right, I'll show it tomorrow in class. So G forces, a G force is an acceleration, basically. When it's an acceleration of your body. So your body has mass. So mass times acceleration is force, and that's why they call it G forces. But 1 G, like I feel like you hear pilots say, well, man, I'll put on 5 Gs. Okay, so 1 G of 1 G of acceleration is approximately, it's 9.81. So you can just round it off and say it's approximately, in this case, 10 meters per second squared. That's 1 G. Now, if you are on a roller coaster, like at Cedar Point, at the Cedar Point in Ohio, that roller coaster, that's a famous roller coaster amusement park. And they have one there that that puts out 4.5 Gs. I've never been there, but so 4.5 Gs. Now a G is 10. So that means and that's Frontier City is probably what, 3 Gs? And a G, if you're on a roller coaster, you go tick, 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 tick to the top, and then you go down. When you go down and you're ready to come back up and you feel really heavy, that's G forces. You can have negative G forces because you go up top and then you feel light, like you don't weigh anything. Or if you go over on a road and you're dab and you're a kid and you go over the bump and woo, do it again, daddy. So everybody that's a negative G. But G's, like in this case, 4.5 Gs would be about the most. You can prove me wrong here on this, but that's probably a pretty high amount of G's for typical Joe. I think it's dangerous after that. people can pass out. That's why they say not pregnant women, you know. So that's 45 meters per second per second. That means that and that you can be a positive or negative, but that's a lot of G's. That's speeding up at 40 or changing directions, more likely. More likely changing directions than speeding up. But because changing directions is also, you know, acceleration. Changing velocity, the velocity vector's direction is also acceleration. But that is a lot of G's, and that's about the most that any human would want to handle. Well, look at this. This bullet is going at 225,000, and 45 is the most we can handle. So, okay, now that's for just a typical person. But how much, I think a student asked in one of the hours, how much can a person handle? Well, in a centrifuge, under lab conditions, and I'll show you a video here, but under lab conditions, they put John Glenn. Now, John Glenn, anybody know who John Glenn was?
The astronaut.
Right, so Mercury 7, right? So he's an American hero, became a senator from, I think, Ohio, or one of those up there. Anyway, so John Glenn was known as the Iron Man. The guy, they put these Mercury 7 astronauts through all these, and it's documented in the movie called The Right Stuff, which I recommend. It's on Prime, I think. Anyway, so John Glenn did 16 Gs and didn't pass out. Most will pass out around 7 or 8. 16 Gs. There's a guy named Stapp. He was actually a doctor. He did supposedly 42 Gs and lived. This is like my numbers here, early 50s, 1948, maybe somewhere in there. He did it on a rocket sled in the desert. And he was a doctor. He worked with these Air Force pilots when they were first becoming supersonic in their jets. And he wanted to see what they experienced. So he strapped himself in and said, light this sucker. And then he stopped. When he stopped, they put him on a braking system. Anyway, the point, he was never quite the same after that, according to some witnesses. A little off after that. But John Glenn did it. No problem. The guy could just handle some G's. So if this right here, though, this bullet is experiencing about 22,000 Gs. So when it comes out of there, out of that barrel, it's metal, so it's a slug, but it's somewhat compressed, even it's somewhat deformed, not like pancake, but somewhat deformed. Okay, and spinning extremely fast. Okay, so all that, we had a discussion today. I wanted to say it. That's enough for that for now. I'll show you a video in a minute. Let's go ahead and knock this one out. And then let's just do B. It said, how many milliseconds will the bullet be in the barrel? So now you tell me, what equation should we throw at it now?
The first one.
Yeah, let's do, you can do the second one or you can do the first one, but the first one's the easiest. So let's just, go for that. Always go for the simplest answer. We're not lazy, we're just efficient. So we say V final equals V naught plus AT, and V naught, of course, was 0. So I'm just solving for T now. And T then is V final over acceleration. V final over acceleration. So V final is 600 meters per second. Acceleration is 225,000 meters per second squared. Notice how the meters per second will cancel. You'll end up with a per second, and that means seconds. It comes up top. It's a reciprocal of per second. And I'll just save you time. This is equal to 0.0027 seconds. But it's asking you for it in milliseconds. See, that's one of those, what's a better way to write? And the better way to write that is not, people don't go around talking, well, that was 0.0027. No, you say 2.7 milliseconds. You multiply by 1,000, which is 1,000 milliseconds a second. So this is 2.7 milliseconds, which is crazy small amount of time. Blink of an eye, probably faster than the blink of an eye. So that's how fast that bullet goes through the barrel. Okay, now we're going to look in detail tomorrow at what goes on inside that barrel. But I want to now switch screens. I'm going to stop the sharing. And I'm going to show you, I'm going to show them tomorrow. This will work. There it is. Oh, share. Okay, so these are pilots, and there's lots. You'll see a lot of these. I like these. I like these guys. I like these. I love, you know, Air Force, Navy pilots. Is this the one I want? Oh man, this isn't the one I want. Hold on. I don't want that one. Let's get another one. Let's try this one. Yeah. I love this guy. I love these guys' attitudes, man. It's this is like, it's all in English, but okay, can you see this? Someone give me a yeah.
Yeah.
Okay, here we go. Let's watch a little bit of it. It's about 4 minutes. Let's watch the first part of it. So these are guys in a centrifuge. And that's what the previous video, okay, let me show you that. In the previous video, they introduced the idea of a centrifuge. This was
farm growth. And the team here are going to push me as far as they are allowed to push a civilian.
The centrifuge has been here since 1955. The device was originally installed for research purposes, although these days it's used for
I don't know how these guys keep from throwing up.
training as much as it is for research. What it does is recreate the forces that you feel in an aircraft. For our routine pilot training, the first time pilots go on the centrifuge, we expect them to get
a lot of it's about their breathing and muscle control.
up to 5G without a G suit.
So 5G, so about 50. So experiencing, like right now, I'm experiencing 1G just sitting here. That's normal gravity. But if I experience 2Gs, it's like having somebody my same size sitting on me. Or if I'm laying down, another one of me laying on top of me. That's 2Gs. So you can imagine 3Gs, now 2 of you are laying on top of you. 4Gs, you see what I mean? I mean, 5Gs, when I have four of me, that's 800 pounds laying on top of me. That's getting to be too much.
And then up to 7G with it.
Okay, I want to go to this other one in a minute. I'll try and remember to put these links in there. Okay, let's watch this. Hope it's not too laggy.
3, 2, 1.
Okay, now somewhere, I can't see, my screen's kind of messed up, but somewhere in here it shows the G's. I think right up there in there, they're using capital, but I don't normally do that. But in the upper left, they're showing the G's.
Engage.
Now watch his face. So there's a lot about breath, and how you're breathing. You're trying not to pass out because the blood goes down to their feet. So the blood pools in their legs. It can cause blood clotting. I mean, it can be dangerous. You don't see old men do it. But it leaves their head and they just end up going out. Here we go.
Your top 3. 1.
Now he's at 8 G's already. See that? This guy's in shape. 8 G's is amazing. But look at his whole face. It's all pulled down because of that G force. Like he aged 20 years.
2, 3. Drop the shoulders. 3. 1, 2, 3. Squeeze your legs, squeeze your butt. Hey, squeeze, keep squeezing, keep squeezing.
All right, there he went. He went out. So the blood left your head, you just go out.
Keep squeezing.
And that's why John Glenn, who did 16 G's, people are just amazed at this guy.
Are you there? How you doing?
Notice he has a little seizure. Because he went to his subconscious, that's the way I've heard it. And so whenever you switch back and forth, you saw that he jumped right there. He does a little seizure in his head. And that happens. Do you ever have it when you're falling asleep? Like you just all of a sudden you jump. That's a little, because it's when your brain, from what someone told me, when your brain switches from conscious to subconscious, there's a little synapse, a little gap in there. And sometimes you just have a little seizure, miniature seizure.
How you doing?
No, no, I,
You know what happened?
no, no,
Huh?
no.
Go ahead and pull back on that stick.
Now you pull back on the stick, and that's what makes you go, you know, round and round and round.
Let it out. Let it go. Nap time. Relax those abs. Drop those
Okay.
shoulders. Relax your legs. Deep breath out. There we go. There we go.
He made it. Oh, there he went.
Oh, yeah.
Okay, he didn't.
There we go.
It'd be fun to do, but I think you'd have a heck of a headache afterwards. Okay, so stop that sharing. All right, so that's kind of cool. Could you hear that? Could you see it okay?
Yeah, it was all good.
Good. Good. Let's see if it's worth sharing. Oh, I got to share one more thing with you, and I'll go back on the screen now, and then we'll call her good for today. Good. I'm glad we can share those because I'll do little clips in class all the time, and I was afraid that we weren't going to be able to do many of those because it's so laggy. But when your videos aren't on, it's a lot better. Okay, so that's what we're going to leave to 11, and then the homework. I showed the pilots. Here's the homework. We're going to do we'll do 212 number 1, 212 number 7, A through C, and then 212 number 8. So you get a dolphin for each. So you get up to 3 dolphins, which yeah, I'm going to go with 2 points a dolphin. So that's 6 points. It's like, you know what? I didn't think about this. I'm going to say, I got to think about this. I'm going to say that you have to have at least a minimum of 10 dolphin points. 20. Okay. Oh, you watch me think here. I'm on 20 dolphin points. 20 dolphin points. Okay. By Christmas break. So you can pull 6 of those tomorrow. Now, anything above that 20 is bonus, and we'll give you enough opportunity where you'll have at least that means it's 10 things I'm looking at between now and Christmas of your homework. Okay, so I guess you'll just hold them up to the screen, and I'll just kind of check it off and say, okay, you get Eric, you get 4, Bennett, you get 4, that kind of thing. All right, tomorrow we'll try that. And going back to look at this now. So we're doing this one, 212. We've already done some of these. We did, that's third hour, sorry. Here we are. Okay, so we did 2 and 4, just 2 and 4. So now you're supposed to do 1, and with 1, if you're in calculus, you have a little advantage on 1. You're supposed to do 1, 7, A, B, C, and then 8. There's a calculus shortcut on 1. You don't have to be in calculus. So 1 is like just doing a little T-chart and then plotting the curve, and then to go back to that, it's going back to that tangent secant stuff again, just to keep that fresh in your mind. And then 7 is fairly simple. 7 and 8 are both pretty simple problems. Don't make them, if you're having trouble, you make them too hard. I'll be available. I'll try and check out Facebook if you have questions. Hope that somebody else can answer your questions. That we're not using it. Maybe we'll use Facebook more. That I'm starting to give you more homework. Okay. So now anything else? I think that's it. That'll be tomorrow. That's tomorrow. Okay. Stop the sharing. Hey, we finished early today because we were a little ahead, actually. Any questions before we say adios? All right, well, you can always ask questions on Facebook. So.
I have a question.
Yes.
So, are the notes packets still in the front porch?
I will, as soon as we get off here, I'll go down and put them on the front porch.
All right.
Wait, you mean the notes? What do you mean? Your notes.
No, like 2.12 and like 2.
Oh, the sheets. The sheets. Yeah, there'll be some stapled 211 through 216. They'll be out there.
All right. Thank you.
Okay.